go ahead and get started. Hopefully you guys had fun running scripts last night, and as I've been talking to some of you and receiving from emails, getting fun error messages. We'll start with those. Just to give a brief recap from yesterday, bring you guys back to this overall picture of where we were started, where we're going, where we're at right now. So we started by downloading our data from the ENCODE website. Again, there are lots of different websites out there that have data. When people publish papers, they put data up on the website. When you do a sequencing run at Illumina or whatever core you choose to use, they're going to upload your data somewhere on a web server. So the point of this first part is you're getting your data from somewhere. We used ENCODE. Then we checked that quality. We went over the FastQC report. And then we've got into STAR, aligning the reads from the genome. Does everybody have a good understanding of what each of these steps is doing, and confident with at least where we've gotten so far in working with STAR and reading the manual? I think we went over this in pretty good detail yesterday. Okay, great. So just one thing that some of you guys were asking me about right away. You'll notice we talked about how when you were looking at the status of your job, you could either see it as running, queued, or complete. So R was to say that it was running, Q meaning it was still in the queue and it hadn't run yet, and C meant that it was complete. But if some of you checked back later and it was like, there's nothing there at all, it's totally gone. So the C for complete will only stay there for a certain length of time. I'm not sure how long it is, maybe 30 minutes, I don't know. But the way that you can tell how your job actually went after that job ID information disappears is using the output files and using the error files that we got. So when we were in class yesterday, all of us submitted a script to generate the genome in STAR. So why don't you guys go ahead and log in and go to the scripts directory where you submitted that genome generate script. So as a reminder, this is what our script looked like. We talked about all of the different PBS tags that we were going to be using to describe our submission parameters. And then we talked about all of the different arguments that we were going to be using to generate the genome. So this is pre-mapping. We have this run mode genome generate, where we provided both the FASTA files from our annotations that we downloaded from the genome browser and the GTF file that we got from GenCode. And remember, when we submitted this script, we specified where we wanted our out files and error files to be called. So you should see those in your scripts directory as well. We also specified this is the location of where we wanted the output of this genome to be made. And we knew that's what this was by reading about the genome dir flag in the documentation. So we read that before we run this script, we had to make this directory, which we called STAR, and then we could refer to it in the script, and it's saying, once we make this genome, put it in this spot. So first thing that I'm going to do is I'm going to take a look at my output and my error files for generating the index. So my error file is empty. Does anybody have an error file on generate index that is not empty? What's your username? What's your number? 09. Do you know why it's there? Do you know
actually, I don't know if that was because that has
Wait a second.
that has actually like that on keys when I was casing.
Okay. Oh, so your error files are not in there. Did you delete them? Wait, you said you're 09? So when you called your script, you must have been in this directory. So I went to his scripts directory, which I showed you here, and ls, and there was nothing in there. So what that meant was when he called his script, he was in this directory instead, which is the star directory buried in Scratch. And when he called the script, you can call your script from anywhere by just giving the full path of the script. So I'm sure he just did qsub /projects lin28 scripts script name. But when you do that, it's going to put the error and the output files in whatever directory you called the script in. So if your error and out files are not in your scripts directory, check the spot where you were when you submitted your script. All right, so let's read his error message. So anytime you get this error that says unexpected EOF while looking for matching syntax error, there's nothing here that is pointing out like a flag was entered incorrectly or a directory was not made. But anytime you get this EOF error, what that means is you have a space or a quote or a dot or a tab or something in a spot where it's not supposed to be. Basically what that means is that your line stringing together your entire code is not complete. You like opened something with a quote, so here it says it's looking for the matching quote. So you opened a quote but maybe didn't close it. So this is a very common error that you'll see, this EOF. And what that means is you have some sort of character in your command that's not supposed to be there. So yeah, you said, how did you fix this?
Well, I figured out that it was because of that weird, I don't know what the character is.
What?
I don't know what the character is, but basically I saw it and I deleted it.
Okay. Yeah. So he went back and looked at his script and saw that he had this character in there somewhere where it wasn't supposed to be. Deleted it and submitted it again. Great. Does anybody else have an error file for the generate index that is not empty? Okay. Who wants to give me a number? Is it, and it looks different than this? Okay, so give me a train number. Who wants to go first? 13. Sorry, whose error message was this? Megana? Okay, so what was the problem with your script in this? Yeah, this is great. So this is a really easy error message to read. It says unrecognized parameter name. So you'll recognize that this is one of the parameters, one of the flags that you were putting into your script, and it doesn't recognize it. That means that there's a typo in it somewhere. It looks for a very specific set of characters, and caps matter. So if you go back to the manual, I'm sure that you will see that you have a capital where there's not supposed to be one, or you're missing one, or you have a typo. How many other people had error messages that looked like this where they could not recognize a parameter name? Yeah, so same type of thing. Just double check that parameter name if there's no typos. All right, new error? What's the number?
404.
Which one is it? This one? So we're on the generating. This is an error for mapping.
Oh.
Yeah, we'll get to those in a second. Did anybody else have any errors on generating the index? Kat? Right, okay, so the QME will show the status of your job while it's running, while it's in the queue, and for like a determined amount of time after it finishes. So remember, I said it will say C when it's complete, but that C will only last there for like, I don't know, 30 minutes maybe, and then it will go away. So you have to refer to the .out and the .err files that you specified in your submission script, and that's where all the information about your job will be. So those are the files that we're looking at right now. Okay. So you should look at the .err file first, and if it's not empty, I'm curious to see what your error message is. Yeah?
So on the thing where like the output error tells me not going forward, you specify the whole path?
Probably. Yeah, I haven't tried that personally, but you can try it. Any other errors in generating the genome index? Okay, so then if there were no other errors, I would expect that your output file looks something like this. Hey, successfully. It's always good when you see that. So you guys will remember at the very end of class, I provided you guys with another directory of where a star genome had already been generated that you could use for your mapping job if yours had not finished yet. But if you get this, where it's finished successfully, you can go check it out in the directory where you put it. So you specified this in your command. So go ahead and check out that star directory that you made and see what's in there. And that's what you will use as the location of your genome directory for your mapping job, as opposed to the one that I provided for you. If you're still having a few error messages with the generating the index, no worries. You guys now know how to read them, so you can hopefully be able to fix them. And you will ultimately get to the point where you can generate this index. But as a reminder, if you still need to use the other location of the index, it's stored in /projects /PS11. That you generated the index? Yeah. So you specified that in your submission script, so let's look back at it again. So if you refer back to the manual with all these flags, you'll read that genome dir is the location where you want this directory to be outputted. So you specified this, we put it in our HG19 annotations directory, and we gave it the name star. So this is the path of what you can provide for your mapping script to go to the next stage if yours completed successfully. If yours did not complete successfully yet and you're still working on it, in the meantime, give it this path. Yep. Okay, that's where we're headed. Okay. Yeah, so no more questions on generating the index before we move on to mapping? Great. All right, so I want to first bring up the mapping script so we can kind of get a reference point again of where we were. So this is what we were doing very quickly at the end of class. I think everybody understood your new submission parameters for the mapping job. We decided that we were going to use, or I told you that we were going to use 8 processors per node, and we were going to give it a wall time of 1 hour. Star mapping is usually very, very quick. So we talked about what each of these parameters means, and now we'll get into, I assume a lot of you have errors associated with this script, and we're going to get into reading those now. Any questions about the parameters that we used? Yeah. Okay, you guys couldn't find this in the manual anywhere?
I didn't see it with all the others, like all the others.
Right. It might have been in an advanced option.
It's like in chapter 9, and I just didn't put anything, because that looks like that's the default based on the...
Okay, okay. Yeah, is that what it said under the flag?
I think it is the default. I guess the default is to use a copy there, I guess.
So let's take a look at the manual
Yeah,
and see if you can find it. So this may be an advanced option. Page 17, thank you. So the default is no shared memory, which would be down here. Each job has a private copy of the genome. So if you were to be submitting multiple mapping jobs, or maybe this is referring to the jobs within the one alignment, it would have to reload the copy of the genome every single time it got to the next step. But what we specified was this load and remove, which means load the information in the star genome that we generated from step 1 and keep it in the memory until it's done mapping. But then when it's done, take it out of memory because we have it stored in a file and we don't need to be wasting that space. So that's, so if that wasn't specified in one of the default options, I've just provided it as an option that we commonly use. And again, if there's something that you're wondering, maybe why your job was taking so long or why it was failing when you were trying to give it a given amount of memory, you could maybe check here and see if there's any ways in the manual that you could reduce the amount of memory usage that you're having with that job. Any other questions about the parameters that we gave this command, about the flags? Okay, so let's start looking at error messages. So, Greg, you had one, train 4.
Yeah.
4. Okay. Exiting because of error could not create the output file, home project slid28 star alignment, log.out. Check if this star alignment path exists and you have permissions to write the file.
I think it's B. After the list 28.
B. Okay, so if you get these error messages and you're like, no, I swear I made this directory, I promise I made it, I promise it's there, the way that I double check it is I just copy the entire path and then go out and I just try to find it with ls, and when I paste it and I go to find it, it says no, it's not there. So the way that you can get the true path that it actually should be is to use your tabs and then copy it appropriately. So if I instead start to use tabs to find this directory, I can ls home, /home, UCSC train 04, projects, lin28b, star alignment. Okay, it's there. I know it's there because I was able to tab to it, and then I'm just going to copy it from this screen to insert it into my script rather than trying to write it in my script manually and likely make typos. Cool. Who has a different error on a mapping job? What's your number?
27.
27. Okay. So you have this gzip at the beginning. What does gzip mean?
But you'll know, it'll tell you.
Okay. So what were we using zipped files for in this script? Anybody remember where we had zipped files involved in our script? Yeah. The original data files, the original FASTQs. So we had a flag in there to use the zipped to read our FASTQs. But what you're seeing is it's trying to read this directory with some sort of zip something. So what do you guys think the problem might be? It should be g unzip if we were trying to unzip the file. But there was a flag in star that we gave it to handle the fact that we were using a zipped file. And it was a read files in command, and I believe it was called gzip or something like that. It's trying to read the files in the wrong place, and why would that be? All right, so he probably flipped the order of where the file location was, which flag was associated with the file location and the flag that was associated with the star directory. So let's take a look at your script.
What I learned last.
All right, so your genome directory looks good. This is the path that we gave it. You also have a read files in, and this path is also the genome directory. So these, remember, are the files in that we're trying to read that are zipped, which are these fast queues, which we're going to put in to perform the alignment on. So go back to the manual and check the read files in flag, and you'll see that you need to provide the full path to read 1 and read 2 as the arguments to this command, not the genome directory. So go back and look at the read files in flag in the manual, and then if you're still not sure what to put in as the arguments, maybe somebody around you who got it right can help you. Wait, raise your hand if you have a different error on the mapping job. No more errors? It was that easy? Okay. Let's see if I got an error. I haven't checked yet. Uh-oh. Error. What'd I do? Path is messed up. I also forgot the B. Whoops. Okay. So I would go back into my script. Well, I'm going to copy the path. Oh, I haven't made it yet. Okay. Yep. Okay.
I did that, but I lost like some of my data files because I created a file that had the same name and like couldn't find it and it got behind. And basically after I just deleted all of the stuff and deleted the whole file. Yeah, it takes a lot of time and unpack
Okay. Who has a star output from their map? So their mapping ran great with no errors. Can you raise your hand and give me a number so that we can look at one of yours? What's your number? 14.
That's why these output and everything from here wasn't intuitive without this. But you don't call out the tasks for where those get made. Those just get made in the final where you call out. But this file.
Okay, so when you look at a successful mapping job in the .out file, finished successfully. Yay! So good job to all of you who got this far. If you haven't gotten this far yet, you should be able to read your error messages and figure it out until you do get this far. And if you're still having any trouble in doing that, raise your hand and Brian, who's here today from the Yale Lab, can come around and help you. Okay, so when we did FastQC, the output files were .html and I had a zip file. So in order to view those outputs, we had to first copy them to our desktop and open them in a web browser because they were HTML files. But not all jobs that give outputs are going to give you HTML files. That was a specific example where we had to use SCP because we couldn't view in a web browser in TSCC. But STAR gives you different outputs. So if you scroll through the STAR manual, they will tell you somewhere where the output, or what the description of the output files that you should have are. Output files, so section 4, page 8. So the .out and .err files that we were looking at, those are files that are generated by the submission to TSCC. Those are independent of the output files that you generate with your STAR script. So we gave the command out file name prefix, we gave it a directory where we wanted these files to be located, and we gave it a prefix so that when it generates multiple of these files, it's telling you the ones that it's going to make here. They're all going to have the same prefix with the same run. So our prefix was Lin28B, yada, yada, yada. Okay, so in that directory, if your mapping finished successfully, you should have a log.out file. And it tells you here, this is going to give you detailed information about the run. We'll take a look at it in a little bit more detail. There's also a log.progress.out file that gets made, and you can see this. This gets updated as your job is running. So it tells you what percent of reads it's aligned and how close it is to being done. So while your job is in the R mode that it's running, you can go and look at this progress file and watch it get updated as the job continues to move farther and farther along. We have a .final.out. This is a very useful file. It gives you the summary of all of your mapping statistics, and we'll look at that. And then ultimately it gives you this align.out.sam file. This is the most important. This is your alignment output. So when I was teaching you guys about all the different files that we work with, the BAM file was the most common alignment file where that stores the information of how it was aligned to the genome. And you guys will remember that the .bam extension was a binary file. It was not human readable, but it was good for compression and storage. I believe there is a flag in STAR if you want to output a BAM file. You can specify that, but by default, it outputs a SAM file. And the SAM file is just the converted version of the BAM file into a human readable format. So it's a little bit bigger, but it's something that we will actually be able to take a look at. And we're going to use some examples with SAM tools showing you guys how you're going to convert between BAMs and SAMs. Okay, so let's take a look at these files. Where did the output go for this user? The output of mapping? Okay, here it is. Okay. So we specified the prefix as Lin28 knockdown replicate 1. So let's Let's take a look at first at the log file, the log.out. And this is where it tells you how the run was done. So it tells you the version of star that you were running. It tells you what default parameters were used because you didn't specify them. If you go back to the manual, you can look at every single one of these, and you can see these are the values that were inserted for each of those default parameters. There's a ton of them. This is really useful. At the bottom, command line. Here's your script. So if for whatever reason you lose the script star mapping that you made, you can't find it, but you want to remember how you did this mapping, you can go to the log file in your output, and this will be here. And then it also talks about the different commands that you redefined as a user here. So all this is basically a summary of the job that it ran in star. Any questions about this file? Let's take a look at the progress file. So this is where it was telling you it's going to update every minute or second, so here's the timestamp. Every minute it gives you a update about where it was. So the read number that it was on, and you'll notice the read number increasing as the job length duration increases. The mapping speed, the length of the reads that you're mapping, and then for each of these sections it's telling you about the quality of how the mapping was carried out. So it's telling you that, okay, in these reads 90.7% of them were uniquely mapped. And we'll get into more detail about what all of these different numbers mean. What the mapped length was, the mismatch rate, what percent of them mapped to multiple locations, what percent of them mapped to too many locations, so this would be more than the number that you specified in your script. They were too short to be mapped or whatever other reason. I don't typically look at the progress file, but if you're curious while your job is running, or if it seems to have been running for a very long time but not stopping, you can check the progress to see if it's actually continuing to move forward or if it's getting stuck on a certain step. Yeah?
Is that speed in megabases per hour? Like if you're trying to estimate how long your run time on the server would be.
Yeah. Maybe? Check the manual. I'm not sure. Do you know what it is? It can't be a million reads because we did 20 billion reads and it took like 2 minutes. Or we did 200 million reads.
Yeah.
So I'm not sure, but you can definitely read about that in the manual. Okay. This is a very important file and something that I always use for all of my experiments. So, when you're running these mapping jobs, you're not just running one, you're running multiple for all of your replicates and all of your different conditions. And this file gives you a very nice summary of how many reads went into your mapping, how many reads came out of your mapping, and what percent your mapping was. And this gives you an idea of if your library was good. So hopefully not too often, you'll get contamination in your library with some sort of other species or something that you're not expecting. And that won't necessarily show up in your FastQC report because it's still DNA and it's still sequencing just fine on the machine, but it's not mapping to the human genome like you expect it to. So here it gives you a good summary of everything that happened with the run. And this also even tells you how many reads came from your run. So some of the most important things that I always look at, and what I do is I make an Excel sheet where I've parsed the output of all of these, and in each row I have a new sample where I've summarized all of these various statistics so that I can look at it all together. So we have a number of input reads. You can see here that we would have, about 21 million reads. This is something that you want to check to make sure all of your samples had approximately the same number of input reads. It would maybe be a problem if you're trying to compare a sample that had 100 million reads to a sample that had 5 million reads. Clearly the evidence that's supporting existence of transcripts is going to be different when you have coverage at 100 million reads versus coverage at 5 million reads. One question that gets asked a lot in the field is how many reads do I need? So the typical standard for just to be able to quantify gene expression is anywhere from 10 to 20 million reads, and you really only need to sequence 50 base pairs single end, because that's enough to give you a unique map to the gene, and all you're trying to do is quantify where that fragment came from. You don't necessarily need coverage of the entire gene, you just need to be able to identify that it was unique to the gene. So typically, to get good estimates of gene expression, we try to target between 10 and 20 million reads, single end, 50 bases. But if you're interested in splicing, in that case, we need more coverage across the transcript because we're trying to get reads that are mapping across splice junctions. When we have reads that actually map across splice junctions, that gives us more confidence in which exons are included or skipped in the final transcript. So typically, when you're looking at splice junctions, we sequence paired end 100 bases, which is what this run was done at. And 20 million is a pretty low end to look at splicing. Typically, we target about 40 million reads. And that's to be able to detect most standard canonical alternative splicing, things that are kind of known. If you're looking for something novel or maybe something rare, you're really going to have to bump that number up. So, for example, in my project, I'm looking for rare, unannotated novel splicing, and in my RNA-seq libraries, I targeted 100 million reads per library. So again, the number can change based on your application. General thoughts are between 10 and 20 for gene expression, around 40 for splicing. And if you're also not sure, you can always, again, keep up with what your field is doing, what people are publishing. They always publish what their read depth was, and then you can kind of go based on that. Okay, so this is the number of input reads that I had. The average input read length was 200, which is great because I did paired end 100 bases. So we already saw this in our FastQC report. This is the number of reads that uniquely mapped to the genome. So here you can see I got, of that 21 million, 19 million of which uniquely mapped. This is a really great number. This is a pretty high percentage, 90%. Typically in our libraries we'll see low 80% up through 90 to 95% is a really great run that we're happy with. If we start to see this number fall to the low 70s, it's okay. 60s and 50s below, it's definitely something that you should look into to say, what are all these other reads doing in my library and where are they coming from? The average mapped length is 197. So this is different than the read length. This is the length that actually gets mapped to the genome. One thing that I mentioned briefly yesterday is that sometimes the end of your reads won't map. Maybe there was a little bit of adapter left over that didn't get trimmed off properly, or low quality at the end of the reads. Those parts will be clipped away if they did not map to the genome. So your final mapped reads will not all be 200 bases if they had to have a little bit of clipping done on the end. So most of them will be 200. You might have some that are 199, 198. Here it's telling us that our average is 197. Splices, I typically ignore this in STAR. There's other splicing algorithms that we use. And for our purposes, we're only looking at gene expression today, so we're going to kind of skip over this. If we have time and you guys are interested at the end, I can introduce another algorithm that we can quantify alternative splicing, which does a little bit better job than this. Percent of reads mapped to multiple loci. So remember in our submission parameters, I believe we allowed for mapping to up to 20 locations. So what this is telling us is 4.39% of our reads mapped to more than one. So these are only unique up here, and these are multiple mappers, but less than the number that we specified in our parameters. And then you'll also notice that there was a percent mapped to too many loci. So only 0.02% mapped to more than what we specified, and those got thrown out. You'll also usually see a percent unmapped because they were too short. In our case, this is around 5%. And then chimeric reads, you guys can read more about that in the manual if you're interested. Basically, those are like picking up translocations or between different chromosomes. And STAR has different filters that you can include in there if that's something that you're really interested in picking up. And so that is included in here as well. So typically when I finish a run, I'll parse my output file. I'll take this number, I'll take this number, I'll take this number, and that's probably about it to give me just a general overall summary of how good my library was. Any questions? Okay. So there's a couple other files that we have in here. We have the SAM file, which contains our alignment information, and we'll do some exercises working with those in a minute. We also have this SJ out tab file, and again, all of this information is included in the manual. This is a tab separated file. It has multiple columns, and if you go check your manual, it will tell you what each of these columns are. This is an output of splice junctions that it detected. So I'm not sure the exact order of all of these columns, but something along the lines of the chromosome start and stop location of where that junction was, and how many reads were supporting the junction one direction and the other. So again, we're not really going to talk about splicing, but just to make you guys aware that this output is here, and if you want to know more about what this file is actually doing, you can read about it in the manual. Okay. So finally, the file that we're most interested in is the SAM file. If you check the size of that file with the human readable format, you'll notice that it's pretty big. So it's 14 gigs. Again, this is the uncompressed version of the BAM, so it's going to be pretty large. BAM files are typically, 2 to 3 gigs, 3 to 4 gigs. But it's also in a human readable format, so you guys can look at it with less. So when you open it up, you'll see a bunch of headers at the top that start with this @ symbol, in addition to, again, the command that you ran. And then you'll start getting into, if you refer back to the PowerPoint where I had an outline of what each of the different columns were, you can see all of that stuff in this file. So if you're looking at something with less, each of these lines is really long, so it's wrapping it around on the screen for me. One thing that I use sometimes to look at this file a little bit more nicely is this -S flag. And what that means is it keeps each line as its own. So it's a little bit easier to read. And now when I want to go to the end of the line, I can just scroll over. And that way it's just easier to keep track of what came from there. So this first column is the read information, the flag, unique identifier to the read. This column right here is the SAM tools flag, and we will take a look at that and what that means here in a second. And then it has the location of the information about where this mapped to. It gives you a cigar string. This is a string of code that's specifying the mismatches, the insertions, the deletions that were associated with this particular read. Yeah?
You say again what the way to do all that is?
Yeah, so that's less with a capital S
Okay.
as the flag. You continue to scroll over, you'll see the actual sequence of the read, along with some other stuff. It's very standard in a BAM format. And then other programs that use BAM files as the input, they are written to access these fields in a very systematic way, because anytime you give it a BAM file, whatever it needs for the program, it knows that it can always find that same information in column 9 in a tab separated file following the headers that all start with @. So some of this stuff is useful to us, but the vast majority is useful just as a downstream user. So one thing that's really handy is this SAM tools flag. And I mentioned at the beginning that if your uniquely mapped percentage is dropping below 50, then you're kind of worried about what's happening there. Star also has an option to output a unmapped BAM. So this will output sequences that did not map. And that can be really useful because then you can look at that unmapped BAM file, scroll over to the sequence, and you can maybe blast this sequence to see where it's coming from. Maybe you have some sort of bacterial contamination in your library. You can also look at these SAM tools flags, which will tell you specific information about the read. So we're going to go to this website called Explain SAM Flags. So this is, again, stored in some sort of code that doesn't really make sense, but there's tools that let us decode it. So if you just Google Explain SAM tools flags, it's going to take you to this page. where you can copy the number of that SAM tools flag. And click explain. And it's going to tell you what that means. So down here are all the options that can be described about that read. So this particular read was paired. So if we had a single end library, this would not be the case. It would not be paired, it would be unpaired. It mapped properly in its pair. That means it found its partner on the other side and it found it within a reasonably small distance. This mate is on the reverse strand. So remember, when you sequence in one direction versus the other, when you go 5' to 3', you're sequencing in the forward direction. When you go 3' to 5', you're sequencing in the reverse direction. So this would be the second read in the pair, and it was sequenced in the reverse direction. And you guys can just check that out with a couple of the other flags that you see in there. All of these numbers are a code to specify the different parameters. So go ahead and play around with that, and you'll see that all of these flags that we have in our file are mapped, and that they're paired because this is paired. This is a different. You might see this flag pop up that's not primary alignment. So this would be included in our file because we allowed for multiple alignments. When it maps to multiple locations, it tries its best to say which one they think is the best and primary, that's what they call it. But if it's mapped to another location, it might be referred to as secondary, so it would be not primary alignment.
By default, how many will it give you if it maps to multiple locations? How many locations will it give you?
By default in star,
Yeah, just give you.
I'm not sure. That's something you'll have to check the parameter. Because that outmax, and that might be a parameter that is required, and it might require you to specify it, or if it's not, it will have a default value in there that it uses. Yeah?
What do you do with like the flag information?
So this is just general information for yourself, kind of as a sanity check to see that what you have in there is what you're expecting. I use this more if I also output an unmapped file and I want to look at the reads that did not map. This is particularly concerning if you have a low mapping percentage and you want to figure out why those reads did not map. So you can use this flag and you can see, you can see that your alignment went okay because all of the reads in your unmapped file will have the flag read unmapped, and none of the flags in your mapped file should have that. So it's just kind of like a general QC thing that you can look at. It gives you general understanding of how well your run went, and if you're trying to debug into things further, figuring out why your results maybe look a little bit weird, this is something that you can do to double check the reads that you actually have and are using in your BAM file. All right. So we're going to try some arguments with SAM tool, or we're going to try some commands with SAM tools, which allows us to manipulate and look at these SAM files. We're going to be converting back and forth between SAM and BAM. So you guys can check out the documentation here. Just to bring us back in perspective of where we are. So before we can go into counting reads and mapping genes, we need to take this SAM file that was outputted and we need to sort it and index it. And what this is doing is making it really useful for downstream programs to operate on that file very quickly. If you notice the file that we've been looking at right now, the reads are in no particular order. See here we have one that was chromosome 1, chromosome 22, chromosome N. These are in no particular order, it's just based on where they were falling in the FASTQ file. So what we're going to do is we're going to sort this file starting at chromosome 1, position 0, all the way down through chromosome Y, position however many there are. And we're also going to make an index file that programs will look for down the line, and an index file will kind of have the instructions on where the reads are located in the sorted file and create like pointers for the program so that it can very quickly go into your sorted BAM file using the index and know where the reads are stored and how to access them. So these are files, or these are the things that we're going to have to do using SAM tools. We're going to have to sort our file and we're going to have to index it. It's for an ordering thing, right? It's speed. Yeah. Yeah, so I guess sorting is necessary for speed purposes because we have 19 million 19 million reads in this file. And if you're trying to, say, quantify gene expression, you're giving it a gene with known coordinates that you have. You have a start and stop location of this gene, and it's on a chromosome, and you want to ask the question, how many reads mapped to that chromosome? So one way that you could do it would be to start at the top of your BAM file and work all the way down and check each line and say, is it within this window? Okay, yes or no. And then keep checking, keep checking, keep checking. But that is incredibly inefficient to do that for each gene that you have, starting from top to bottom of your BAM file. So it's much more efficient if we can do it when we have the BAM file in a sorted fashion, knowing where that particular region of the chromosome is located within our BAM file so that we only have to check that region. It's a speed and processing thing for downstream steps.
A lot of bioinformatics is set up to help you design your structure of your data, and it can be the exact same data, but define the structure in a more efficient way, so you can do actually more things later, faster. That's probably why we use this.
So there's a million different ways to do things, and that's definitely one way that you could do it. You could take your gene locations and you could go from your BAM file from top to bottom and look for things that map to that gene. But people have figured out much smarter ways to do it, and that's what a lot of these programs rely on. Okay, so I have some instructions for this in the 5th workbook that's available in the Google Drive. So you can check out the SAM tools documentation, and it will take you to this page. I personally think this is one of the nicer documentations out there. It's very useful, and I think it's written fairly simply and easy to read. It starts with an overview of all of the different tools that you can use. So SAM tools sort is a function, SAM tools index, SAM tools IDX, stats, and da-da-da. As you continue through, it gives you a description of what each of these things are doing. So SAM tools view allows you to view a BAM file because BAM files are non-human readable. We need a tool to be able to view them. So you guys don't have one right now, but I have some in that directory. So I want to, let's see. You guys should be able to go into here. I have other BAM files. So if I want to view one of them, I can use SAM tools and pick any of the BAM files. And this is going to throw everything onto my screen. This is a very big file, so I want to pipe it into less so that it will become scrollable. So now I can view that file. And remember, it had the extension BAM. So we didn't have to do this with our star output because it was a SAM file. But you will also be working with BAM files. So SAM tools view is a really nice one to be able to view it. And if you guys want to try these out on your own, the directory is the same as this, except just not star. So you guys can check out the BAM files in this directory to try a couple of these commands. Yeah? Oh, sorry. Okay. Use tabs. Also, SAM Tools is a program that you guys remember we installed on day 1. If you don't remember if you've installed it, you can check. And if you want to make sure that the documentation that you're looking at is right for the version that you're running, you should also check your version. Okay. So SAMTools view is a nice one. I do that a lot because once we make these files, we store the final ones in BAM format as opposed to SAM format because it's smaller. But if I want to look at them, I have to use SAMTools. I'm not going to go through all of these. You guys can go through them more on your own. SAMTools sort is one that we will come back to. We're going to do that on our file. SAMTools index is the other one that we're going to do on our file. I really like this one, SAMTools flag stat. And you can actually do this on the file that you made because it will, well. So here is an example of the syntax. SAMTools flag stat is the command. And you'll notice that there's no dash, dash, anything, or dash followed by one given character. There's no flags that you need by default. But what it's saying here in italics is in dot something. So this is your input file. So you can either give it an in.sam, BAM, or cram. And I actually don't even know. Do you guys know what a cram file is?
What?
Cram file. No, never really use it. SAM or BAM. So all you have to do is SAMTools flag stat followed by your file name. That's how you read that syntax. And then it tells you what it's gonna spit out. So if you go back into your, you can do this on your file. Take a long time. It might take a minute. But what it's going to give you is really nice. It provides counts for all of these just kind of general QC things. So it's going to tell you how many of your reads mapped, how many of your reads uniquely mapped. This is another way that you can get it instead of having looking in your log file from star. So if I need something in a program downstream that asks me how many reads were mapped in my BAM file, I can get it very quickly with SAMTools flag stat. Okay, and this is going to take a minute, so if it's not working for you, don't worry about it. This is a little bit memory intensive, so we're going to end up writing scripts to do the rest of the SAMTools commands that we need. Okay, so I want to give you guys a minute on your own to figure out what the commands are going to be that we're going to need to use for SAMTools. So there's two that we're going to have, SAMTools sort and SAMTools index. And I want you guys you can work together and help each other out to look through this documentation and decide which flags you need to use and what your syntax is going to look like for the final command. So you'll notice here, SAMTools sort is the command, and it has in brackets, meaning these are arguments that you could use. And it has, again, the syntax that we're familiar with. We have the dash L or dash whatever. So these are the various flags, and you can look at what those are. They have defaults as well, so maybe the defaults will work for you, and in that case, you won't need to include the flag. And then you'll notice at the very end, it's that same format with this in.bam sam or whatever it is that you want to give it, and there's no flag in front of that. So the way that you read that is after your last flag, so you would have a dash at symbol, space, your number of threads, then you would have another space, and just simply give it your input file. You don't need to give it a flag in front of this one because there's no flag specified, it's just your file. All right, so why don't you guys just work with SAMTools sort right now, talk to each other about what flags, or what this final script is going to look like. You guys can write this with VI, you can write it on a piece of paper, in a text editor, whatever you want, to see what the syntax and how you're going to sort that SAM file that you just made. Okay. And help each other out. Don't cheat. Don't cheat and look at the thing. I already put the answer on there, but don't cheat. Start at the documentation and try to figure it out on your own. Yeah. Yeah, so I'm going to tell you what. So when you think you have your sort script, make a submission script, make a .sh script. These are the parameters that you guys can use. And don't submit it yet. We're going to go over it together. We're also going to add something else to the script before you submit it. So don't submit it yet, but go ahead and add your command into your script. So if you do not have a SAM file yet, if your script has not finished mapping, still go ahead and figure out what all the flags are that you're going to use, and I'll give you a SAM file that you can use.
Okay, so I will then output file.
So usually,
And then all I do is put the file name and one here. Oh, yeah, sorry.
This is the full path of that file if you don't have one yet. It's in the same directory. Use tabs. This is what that directory looks like. You'll notice I have a bunch of other stuff in there, but the one that you're going to want to use is this align.out.sam. This is the direct output from star that everybody else is working on. So I wrote that on the board over there. And remember to use tabs to help you make your life easier.
Okay. Oh, that's Yeah, I got it.
Well, it's